Okay, now the start of our particular webinar, the why. Hopefully the clue in the photo there, water is not our friend. Water is a particular problem for structures, and if it's not managed properly, it can lead to lots of problems, which I'll discuss in a bit more detail. This is not an engineering lesson. We're not back to college, guys, but you've got different examples of bridges here. And they've all got one thing in common. The bridge deck is fundamental to how these bridges function, to how they perform, to how they operate throughout the service life. So we're talking today about protecting our bridges. Now, segmental concrete bridges are quite a popular method of new construction. But one of the I wouldn't say downsides, but one of the effects of this type of construction is that the decks are quite lively. They impart cracking. So whatever you do in terms of your protection, your membrane needs to have the ability to withstand movement and cracking. If it's a rigid type of system, then very early on, you may find you're going to get cracking and flexibility issues. I'm not here to frighten anybody. We've all seen the horror shows of bridges collapsing, and that is obviously a complete worst case scenario. There are many bridges out there that are 150, 200 years old that have never moved anywhere, and they're still okay today. But maintenance, good practice, looking at the right materials and methods used, regular inspection, and proper recording and measuring of structures is vital. If we get it wrong on a bridge, it can be fatal. You know, roads can be repaired, but a bridge, you get your post-tension, your tendons going, it's not good news. So we need to focus on that bridge deck. It's not going to protect itself. It needs to be adequately protected moving forward. So this is our bridge. There are clearly hundreds of elements to the bridge. Today we're talking about bridge deck waterproofing, which is covered with asphalt 9 times out of 10. There are specialist bridges out there, swing bridges and bascule bridges that have got their own special wearing courses, but that's not for today. A bridge has expansion joints to cater for the movement. It has bearings, again, to cater for the movement of the structure. There's probably going to be piled underneath with foundations. Drainage, very, very important, and it's something I'll talk about later. Water management, don't forget it. Anti-carbonization, protecting the sides of the structure, again, to stop corrosion on your soffits and that sort of thing. Okay, so why are we waterproofing bridges? Why is it so essential? And I'm going to talk a little bit about the shortcomings of some types of system. Again, I'm not here as Mr. Hatchet to try and discourage anybody from using any type of product. This is not that type of webinar. I'm not selling products here. I'm giving you information and education and experience of this particular field. So wherever you are in the world, at least one of these will be a factor that will influence the performance, the longevity, and whether or not a structure is going to suffer from corrosion at an early stage or later on down the line. It could be extreme temperatures. Some of the guys on the call, maybe in the Middle East, where it maybe gets to 5 or 10 degrees in the winter, but 55 to 60 in the summer. Maybe guys from Asia Pacific, where it's very, very humid. Or maybe from Canada or Eastern Europe, where it gets very cold. So there are impacts there from temperature that can cause the structure to expand and contract, that leave paths leave areas vulnerable to penetration. Airborne contamination, that may be pollutants from the vehicles, from the traffic, from marine pollutants, and obviously waterborne contamination from rainfall. All of these put together can create serious problems with the concrete or steel. Now here's one early sign of that. On the right there, you can see that we've got cracking in the concrete, we've got fissures, we've got capillaries, voids, where water and other contaminants can enter the structure. They will be pushed down into the structure by the traffic. And once they get down to the reinforcement will eventually start to corrode. Then it expands, the concrete around it will start to spoil, and then you start getting structural problems with the particular bridge. So that's the sort of cycle that we can get with corrosion. Now, if you are a bridge owner and you have corrosion on your particular asset, then you've got quite a number of headaches to deal with. There's the repair and maintenance of that particular structure. You've got to stop the traffic. You've got to divert that public another way, or certainly reduce the flow on the structure. You've got to expose the deck. You've got to remove the asphalt. You've got to remove the waterproofing if there's one. You've got to do chloride inspections and remove any failed concrete. All of this takes time, cost, and disruption. If you get corrosion, and we're all there designing our structures today for maybe 70, 100, or even 120 years. And if there's corrosion in the first 15 or 20, then clearly it's going to have an impact on the service life of your particular structure. And there's a high cost of remediation, as I said, closing the bridge down, or even the tunnel down, diverting traffic, or, it's a major, major headache, particularly if this is a vital artery to a particular city or town. So all in all, not a good situation if you're a bridge owner. I'm now going to move on now into the types and methods of waterproofing. In a little while, I'm going to talk about the history of waterproofing. But waterproofing began, if you go back to puddle clay, we're going back thousands of years, and mastic asphalts and things like that have been used a long, long time. But in sort of 40s, 50s, 60s, and the present day, we are still using torch-applied, pour and roll, or self-adhesive type bituminous membranes. Now, these are preformed sheets, which are generally about 1 meter wide. And every time you put a roll down and you overlap it, there's a weak spot for water. So everywhere, every 1 meter, there's 2 laps. There's also a lap at the end and that end. So there's 4 locations where water can enter that structure. Not easy. Now, I used to be involved in this on roofing many, many years ago. And a lot of these membranes are 5 and 10 millimeters thick. To dress them into a drainage area, to dress them up and upstand, to deal with expansion joints is not easy. And a lot of the time you leave voids, you leave areas vulnerable to percolation later on. Mastic asphalt is where I started my career. It's a great material. Environmentally, number one. It's a natural product. But what it is very hard, which is great, for things like steel bridges as a wearing course, no problem. But on a concrete bridge, the bridge will be too lively. There'll be too many cracks. The material won't withstand that. The only way you can use it, you'd have to use a debonding layer, which defeats the object. Because if the mastic gets perforated, water can just track and find its way through the structure. So it's not a great material for concrete bridges. That's all I'll say on the subject. These are, the common name is stick and lick, which is preformed self-adhesive type. And again, they're quite laborious. You know, if you're a bridge owner or a contractor and you've got to complete a section of bridge quick time over a weekend or even a night shift closure, then it's going to take you time. It's going to take time to do this. Now, they're also vulnerable to penetration or damage from hot asphalt. Hot asphalt, the clue's in the sound. It's hot, and there's aggregates in there that will penetrate these types of material, unless you're using quite a robust protection layer, which is another layer and more time and more cost. So these types of systems are still used. They are relatively inexpensive to purchase. Installation, it will probably cost you more because it takes longer to install than compared to the higher performance. But generally speaking, these are considerably less expensive on day one to the high performance systems. Now, day 1000, it might be a different matter if there are problems with leakage and durability, but bear with me on that. Now, just to prove that I'm not here flying a flag for all things high performance, these systems that are commonly used today, these have been about maybe 35, 40 years now, so they're not new by any means. Because it's higher technology, using specialist machines, specialist mixing, and you need skilled guys, there's always a potential for something to go wrong. And you can see here on the left, you've got two particular coats of material that aren't bonded. So you've got what we call intercoat delamination. So it might be bonded to the concrete, but it's not bonded to itself. So not great. In the middle, we've got what looks like a cheese slice, but in effect it's not. It's a piece of membrane, but it's over thickness. It's well over the prescribed 2 millimeter thickness that is required on most projects. And that's lack of control, lack of supervision, lack of monitoring. Now, a preformed membrane is a set thickness. You can't go wrong. But with a liquid system, you've got to make sure that it's applied properly, monitored, regular thickness checks done to make sure that we don't get these cheese slices. Product mixing, again, the two component materials. If there's too much part A, not enough part B, you're going to get blisters. So again, you need to monitor that and make sure that you've got the right people on site, the right equipment, and the guys know what they're doing. The final one could be any type of system, but that's poor preparation. The membrane is debonding from the concrete because of lack of care and attention. So these are some of the things that can go wrong. Now, I'll let you into a little secret. The weakest part of this application is bonding to asphalt. Why is that? Well, you're trying to bond, in most cases, polymers to bituminous materials. And that's not easy. It's certainly not easy when you've got heavy traffic loads, which is increased shear forces, and high degrees of temperature differentials as well. So this is where you need to get it right. Most people, most systems can bond to concrete. That's the easy part. Bonding to asphalt, that takes a bit more skill, care and attention and thought. So it's very, very important to avoid these scenarios. And what you've got here is slippage. And that's because either a combination of its bond to the concrete, so it's shearing from the concrete, or it's shearing from the asphalt itself. So the asphalt's moving under the braking forces. And it's commonly known as alligator cracking, certainly in America. So, and that's caused, as I said, because of the lack of bond between the two materials. So it's very important that whatever materials you're using are compatible with the overlay, and also that the asphalt grading, mix design, thickness, and temperatures are reviewed and controlled and approved before they're allowed to be used. Very important. Now here, again, is what can go wrong. On the left, you've got a very open textured, voided asphalt material. Now, if you're trying to bond to something that's a relatively smooth surface, then applying an asphalt that, again, has a relatively smooth interface that's not like a honeycomb, that's what you're trying to get. You're trying to get a smooth interface so you get optimum adhesion. But here, you've got mixing problems, you've got too much aggregate content, lack of compaction, probably lack of temperature, because a lot of these systems have got a reactivation temperature for the bond coats, which I'll go into a bit more detail later. So there's a lot that can go wrong. But there are simple guidelines to make sure it doesn't. But in these particular instances, the recommendations have not been followed, leading to premature failure of the overlay. So when you're looking at waterproofing systems, what are your design considerations? You sat there in your office, you're designing a specification, perhaps, could be anywhere in the world. Abrasion resistance, why is that important? Well, your membrane is going to take vehicles when you're laying the asphalt. It's going to take workers. It's going to take equipment when you're laying things like curbs afterwards. The overlay, maybe the drainage. So it needs to be robust and resistant to abrasion. Crack bridging. Concrete will do two things. It will go hard and it will crack. So your membrane needs to be resistive, not just once, but throughout its service life. No point having a really flexible material that doesn't come back to its original shape. So that's important as well. Rapid installation, as I say, most of these jobs aren't manana. They need to be finished in a set timetable to allow the asphalt to be laid, to allow the bridge to be open. So we don't want something that's going to take forever and ever and ever to install and multiple layers and whatever. So that is important on a lot of projects, the installation speeds and processes. You can read the other ones. I don't want to go into every one, but it might be important for fire on a particular job. If it's an underpass that goes into a tunnel, for instance, your membrane needs to be more resistive to fire, certainly if it's exposed. If it's covered with asphalt, probably less so. Resistance to heat and damage from asphalt. I'll talk to you in a minute about some studies that were done in the UK. And they found that looking at maybe 25 or 30 different types of system, the vast majority were failing at the time of asphalt installation. So they were being damaged when they were laying the asphalt. So they were failing from day one, in effect. So whatever you use needs to be resistive to that overlay. Water tightness, it's a fairly obvious one, but there are a lot of materials out there that are used that aren't particularly good waterproofing. On a bridge, you'll not find out today. You'll certainly find out in a few years' time that water will get through, percolate and start causing corrosion. Chemical resistance, you've always got fuel oils, you've always got chlorides in certain environments, whether it's marine or de-icing salts that's used. So these are very, very important for any particular specification or design that you're doing.